Okay, we have 14.7 here, and 14.7 is a little bit of a confusing problem. I think it's easy to understand the setup here. We have a 10 kilogram block, 6 newtons applied to one side, and it initially starts out by moving 5 meters per second. And we're wanting to know what the final velocity after it moves 10 meters here horizontally. All right, but there's a catch to this, right? There are two observers to this. We're trying to find this problem for someone just standing on the ground and not moving and just observes this moving 10 meters. But then it also wants us to find the velocity in a moving inertial reference frame, where you can think of the observer B as being maybe on like a cart and is moving 2 meters per second to the right here as this thing moves, and watching this thing move as the observer is actually moving on a cart at 2 meters per second as it's going to the right. And it kind of wants us to compare these two answers. So let's start out with the fixed inertial reference frame, and I think that's the easiest one. And our equation here, remember we have the kinetic energy plus the work done from 1 to 2, state 1 to state 2, equals the kinetic energy at 2. All right, so we know initially it's moving at 5 meters per second, and it's a 10 kilogram block, so we have 1/2 times 10 times 5 squared. And the work that's being done, right, that's the 6 newtons here over the 10 meters. So we have 6 newtons being applied over 10 meters, so that's 6 times 10. And that is equal to the kinetic energy at time 2, or state 2, 1/2, and the mass doesn't change, it's still 10, and that's V2 squared. And solving this problem, we have V2 is equal to 6.08 meters per second. Okay, so that's our first part of our answer, and that's for the fixed reference frame. All right, so now we need to talk about the moving reference frame. And we have this velocity of B with respect to A, observer A is 2 meters per second. So this person's moving on a cart as this block is moving. And we first need to figure out the acceleration that this thing is moving in a move. So we have, remember, just F equals ma here. And the force that's being applied is 6 newtons, and we have 10 as the mass. So solving this equation, we have the acceleration is 0.6 meters per second squared. So why do we need to know that? Why is it important to do that? Because we need to know the time it takes. We're trying to figure out the time it takes to travel this 10 meters as well. And to figure out the time, remember we're going to use this equation. S naught plus B naught times t plus 1/2 a constant acceleration t squared. Okay, subbing in what we have here, we know we want the time when it goes 10 meters. It starts from 0. We know the initial velocity is 5 meters per second, and we just figured out the acceleration is 0.6 meters per second squared. And solving this equation here, we have the time it takes to travel those 10 meters is 1.805 seconds. Okay, so why do we need to know that? Well, in a moving reference frame, right, it's not going to appear, if we're an observer moving along with this block, it's not going to appear like this block moves a full 10 meters because we're also moving. So we need to convert this into our reference frame. So how far are we going to move as an observer, maybe on this cart as it moves along there. So as the observer, let's call this S prime, the distance that the observer on the cart moves, and we know that they're moving at 2 meters per second. And how long does it take to travel that at 10 meters? It's 1.805 seconds. So the observer is actually going to move 3.609 meters. So to the observer, for this block to move 10 meters, the observer is also moving. So the block moves, is going to appear that it moves the 10 meters minus the amount that the observer moves, the 3.609, which comes out to 6.391 meters. Okay. All right, so let's use this equation for energy here, our work energy equation. So we have T1 plus the work from 1 to 2 equals T2, and we know T1 is 1/2 times the mass, which is 10, times the velocity, the initial velocity. Well, if we're in a moving reference frame, right, of 2 meters per second, the initial velocity is actually 5 minus 2, which is 3. So we have 5 minus 2, and don't forget to square that. Oops. Plus the work that's being done, and that is 6 newtons. But the distance here, right, is this here, this 6.391 meters, not the full 10 meters. And T2 then is 1/2 times 10, and V2 squared is what we're trying to find. Now, solving this equation out, we have V2, which comes out to be 4.08 meters per second. All right, so that's for the moving reference frame. And if we take a look at our answer from part A, or the first part, right, the difference between these is actually 2 meters per second. So these equations work no matter what inertial reference frame we're using. Okay? As you can notice here, they're 2 meters per second apart, and that is actually how fast the observer is moving.